Let us say we have a dipole P which makes an angle theta in a uniform horizontal electric field. Then in such a scenario, torque will be exerted, we know, and because of that the dipole will tend to align with the direction of the electric field. Now when it tries to align with the direction of the electric field, no torque will be exerted. However, the dipole has gathered some kinetic energy of rotation while it rotated in order to align itself with the direction of the electric field, and because of this kinetic energy it will overshoot like so, and then the torque will be again restoring. Then again it will try to come back, and then again it will overshoot, and hereby it will reach its original position, and then again the torque will be applied on it. So we can intuitively see that this is somewhat like an oscillatory motion. Torque we know happens to be equal to P cross E. So here we are writing it down as Pe sin theta. Now we make the small angle approximation and say that theta is small. So when we are able to say that theta is small, we can write down torque as Pe theta, and this we will note is restoring torque. So if theta is the displacement, the direction of torque is opposite to that of the displacement. So the sense in which torque gets applied is opposite to the displacement theta, and thus we can write down torque as I times alpha according to Newton's law, and I alpha is going to be equal to Pe theta. Therefore alpha will be equal to Pe divided by I times theta in this small angle approximation. So we are already making the small angle approximation. So this step is the step wherein we made the small angle approximation. Alright, so this is what we get, and we already know that this is restoring torque. So this looks exactly like simple harmonic motion, and this is going to imply that alpha is equal to omega square theta. I am skipping the negative sign over here that is customarily written down because it is understood that the torque is restoring, or we can now put in the negative sign, and omega happens to be equal to root of Pe divided by I. So this is the angular frequency with which the dipole oscillates. The dipole is actually oscillating, as we have aforementioned, from this position to this position to this position, then this position, then this position. So this dipole is oscillating like this in this particular electric field, and we have assumed that this angle theta is small. So small theta approximation has been made over here.